Yesterday I told you that there is this beautiful idea about just one function psi t, it dilates and translates going all over to capture incremental information. Now, we need to state that formally too, but in order to move in that direction, we first need to bring in, as I said, another function which will span V 0. So, we need to bring in this idea of spanning. We say a set of functions, let us say f 1 to let us say f k and so on, span a linear space if any function in that linear space can be generated by the linear combinations of this set. Now, again there is this subtle distinction between finite linear combinations and infinite linear combinations. I do not wish to dwell on those distinctions at the moment, but what we are saying, what we mean by span. So, when we talk about the span of a set of functions, we are talking about all linear combinations of those functions, and therefore, the set or the space of in fact, the space of functions generated by all linear combinations of that set. So, now we ask a question which should make our life easy. What function, we asked this question before, but now we answer it. What function, suppose we call it phi t and its integer translates span V 0. And the answer is very easy. In fact, if you were to visualize a function which is 1 in the interval from 0 to 1 and 0 else, lo and behold, you have the answer. So, what we are saying is any function in V 0 can be written like this. Summation n over all the integers C n phi t minus n. So, essentially integer translates of phi. And these are the piecewise constants here. Just to fix our ideas, let us take an example here. So, what we are saying is, for example, suppose I have this example of a function in V 0, all right. So, I have 0, 1, 2 and 3 and so on. The value here is, let us say 0.7, the value here is 1.5, the value here between 2 and 3 is 1.3, the value between minus 1 and 0 let us say is 0.2 and so on, then and this could continue. Then this function can be written as well plus 0.2 times phi t plus 1 plus 0.7 times phi t plus 1.5 times phi t minus 1 plus 1.3 times phi t minus 2 and plus and so on. Simple enough, not at all difficult to understand. So, we have this single function phi t whose integer translates span v 0. Now, the subtle point is that if you were to go to any space v m, so the same thing would carry forth. So, it is very easy to see that any space v m can be similarly constructed. In fact, we can be more precise. We can write down V m is essentially the span over all n belonging to z of phi 2 raised to the power of m t minus n. So, just as we looked at the wavelet yesterday and said it is this single function which can allow details to be captured, we now have this function phi t which captures representation at a resolution. It is a very powerful idea if we think about it. If you want to capture information at a resolution, at a certain level of detail, that is all the information up to that resolution, you have the function phi. If you wish to capture the additional information in going from one subspace to the next, you have the function psi, the wavelet. Now, we need to give this function phi t a name. We shall call it a scaling function. Now, of course, here the phi t that I have drawn in this context is the scaling function of the Haar wavelet or the Haar multi-resolution analysis. Now, what is this multi-resolution analysis? I have suddenly brought in this word. So, what is this? Well, this ladder of subspaces that we are talking about here, with these properties, is called a multi-resolution analysis. Or an MRA for brief. Of course, in this case the Haar multi-resolution analysis. Now, what properties? We need to put them down formally once again. We have introduced two of them and one more subtly, but we now need to put down axioms very clearly. So, let us put down what are called the axioms of a multi-resolution analysis. So, the first axiom is of course, there is a ladder of subspaces of L to R. and we know what that ladder looks like. Such that axiom number 1, union over all integers closed V m is equal to L to R. Intersection over all integers V m is the trivial subspace with only the 0 element. These are not all. Further, there exists a phi t such that V 0 is the span over all integer n of phi t minus n. Point 4. In fact, it is not just span, there is something more. These phi t minus n over all n is an orthogonal set. This is a deeper issue here. Now, we will explain in more detail the notion of orthogonality in the next lecture, but for the moment let us be content to put this down as an axiom. Next, if f t belongs to V m, then f 2 raised to the power of m t or 2 raised to the power minus m t belongs to V 0. So, for example, if f t belongs to V 1, then f t by 2 or f 2 raised to the power minus 1 t belongs to V 0 for all m belonging to z. And if f t belongs to V m to V 0, then f t minus n also belongs to V 0 for all integer n. So, these are the axioms of a multi-resolution analysis. That means, this is what constitutes a multi-resolution analysis. And here we have taken the Haar multi-resolution analysis to build the idea up, but the whole abstraction is that we can have several different phi's, and then to end this lecture the corresponding psi's. So, where does the psi come in? It comes in what is called the theorem of multi-resolution analysis. Given these axioms, there exists a psi belonging to L to R, so that psi 2 raised to the power of m t minus n for all integer m and all integer n span L to R. This is a very, very significant idea. In other words, this is exactly what we said yesterday. Take dyadic dilates and translates of the function psi, and you can cover all functions or can go arbitrarily close to any function in L to R as you desire. We have built this idea up from the Haar example, but in the next lecture we shall try and build a little more abstraction into what we have done and proceed further from there. Thank you.